Hello everybody, and thank you for joining me today. I'm Lula Zorovic, a developer advocate here at Near4j. In this session, we will have a brief reminder as to what a graph is. We will look into why graphs are important and why we need them. Following on, we will look at examples that will help us to start thinking beyond more traditional questions we may ask of our data, but also thinking about graph-shaped questions that lie there. We will then move into exploring 4 scenarios that can help us spot and identify graph-shaped problems. So for those of you who perhaps have not come across specifically graph or graph theory, when you think of a graph, maybe what triggers in your mind are visions of bar or pies or other chart-based visualization. And whilst these may be referred to as graphs, in this context, the context that we're going to be looking at today in these slides, and when we talk about graph databases, we'd refer to these visualizations as charts. So what is a graph? A graph is a When we think about graphs and what a graph is, what we're doing is we're defining a graph as a way to represent a set of discrete objects or entities. And then we want to think about how they're connected to each other. We want to understand how they're connected to each other based on their relationship. And this concept of graphs arose from a mathematician called Leonhard Euler, who came across this problem that was published in a newspaper. And effectively what he did was he took this problem, which was understanding how somebody may visit these 4 land masses and how they would access these land masses via bridges. And he simplified that down to identify the land masses as these discrete objects and the bridges between these discrete objects as the relationships, the connections between them. So absolutely anything can be a graph. And let's look at a couple of examples. So the internet is an example of a graph. And there's many ways that we can look at how the internet is being represented with a graph. So perhaps we're interested in the different things that constitute the internet. So maybe we are interested in the web pages, maybe we're interested in how emails are being sent, maybe we're interested in the other way, such as messaging systems and so forth, are sending data around. Maybe we want to look at how the internet is represented by the components that put it together. So maybe we're interested in the routers, the switches, the firewalls, everything down to the bare wire and the boxes that connect it together. For example, a water molecule can also be represented as a graph. So if we think about the discrete entities that we have in the water molecule, we have an oxygen element and we have hydrogen elements, 2 hydrogen elements. And it's what tells us it's water. It's not just those elements on its own, but how they're connected to each other. And there is a specific way that these elements are connected together that tell us that this is a water molecule. So you can get a flavour that anything can be represented as a graph, and it's all about understanding how different discrete entities are connected to each other. So why do we need graphs? Why are they important to us? So what I want to do is walk through a snapshot of a situation, and we get a flavour for how graphs can be very useful. So let's say we've got a certain situation here. So here we have a person drinking a coffee. And maybe the reason why we're interested in this is because they're not having a coffee just anywhere. They're sat at a cafe. So maybe we're wanting to keep an eye on that behaviour about how people are using a store. And what we want to do is we want to find a way of being able to represent this reality in the best possible way. So inevitably, if we're thinking about how we want to go about describing this situation, modelling this situation, so that we can think about how we're going to ask questions off the back of this data once we've loaded it into our data source, we would probably start off with having some kind of a representation for a person, we'd have some representation for the coffee, and inevitably we're going to draw some kind of a line or an arrow between the two to say that they're connected, and we can further describe that in some way to sort of effectively provide some kind of pictorial representation of what's going on in our snapshot. And what will happen? So once we've gone away and we've sort of described the connections between our data, we're probably going to go and take that data and put it into a data store. And your more sort of traditional data sources, your relational data sources, what we will do is we'll take this data and we want to go away and normalize that data. And we do that for good reason. You want to reduce the duplication in your data, for example. But the challenge that you have here, so you end up with taking each of those entities and we've put them in separate tables, these discrete tables, and then we need some kind of a mapping table to be able to reconstitute that data back again. And the challenge that we have here is that doesn't really describe what's going on in this sort of scene that we were trying to describe. Another challenge that we can face as well is maybe the data that we're interested, the entities that we're interested are living in different domains. So we've got different data domains, so they're being stored in separate systems. And we have that challenge about how do we represent this reality of what's going on? And we want to think of a way of how do we connect these things together? And what we find, and we come back to this sort of thinking around what a graph is and what it does, and the fact that a graph is a representation of discrete entities and how they relate to each other. By using graphs, we can create something that provides a better approximation of the reality of our data and the questions that we're looking to answer. So we've talked about what a graph is and why we need them. And what I'd like to do now is explore an example to help us generate some ideas about what might and might not be a graph-shaped problem before we step into having a look at some scenarios to help us categorize graph-shaped problems. So let's imagine a coffee chain. So we are interested in a coffee chain. This chain has many stores across the country. We have a mix of things that we're selling. So we've got products that we directly source from our suppliers. Maybe there's certain products that we sell in store that we create in store. So for example, the coffee, or maybe there's some things such as any baked goods or things that we sell in there. And those are being kept in our regional distribution centres. So that's the way we efficiently distribute our goods around. And also we'll be sourcing ingredients from our suppliers to those distribution centres as well. So if we wanted to understand the overall health of this company, what was popular with the customers, what was the footfall and so forth, we may think about asking certain questions such as, what's the turnover? What's the profit margin? Maybe we'll have a look at what are the most popular selling products. Or maybe we want to have a look at when, what number of orders were being placed in a certain period of time. And whilst we could ask these questions of a graph database, these aren't graph-shaped problems. These are typically going to be some form of data summation or data windowing, or we're running some kind of an average over the data, and that's going to be data associated to a single type of entity. But what if we look a little bit deeper? What if we could look further into what drives revenue or profitability, or is there something that we can do to perhaps influence or push those? What if there was something we could do to understand the connections behind why some products are more popular than others or not? Is there some kind of interaction where a product on its own doesn't sell well, but if that product goes with another product, then it does very well? Or maybe there's some kind of a pattern behind the footfall over certain periods. So thinking about these, where we might start looking about, so where do we find these graphs in coffee? So what I'm going to do is have a look at some conceptual examples of graph problems that we might want to explore. Perhaps we have many pastries left over after the breakfast run. We could improve our profitability if we could sell them outside of the most popular time. So perhaps what we can do is investigate relationships between products or how things have sold better in the past, and examine that relationship between product and product, or products and customer, to perhaps tailor some kind of special offer to help us better sell those products outside of the peak times. Maybe we can have a look at how our customers interact with us, both in person, maybe over social media channels. Can we have a look at our customers and have a look what kind of networks do they have in these social media channels? And if we can identify those influential people in the networks, can we do something, or can we encourage them, or do we ensure that they've got a good experience so that they provide positive feedback about our stores to their networks? Well, we've looked at sort of positive sides of what we can do, but how do we look at things where we might need to do some mitigating behaviour if a challenge comes up? So, for example, what happens if something happens to a product that we sell? So maybe there's a product or an ingredient that we use and our supplier no longer provides that. So what we can do several things. We can look at the relationship between that product and the store. We can look at the relationship between that product and others that are purchased with it. So is this a product that, you know, is influential in promoting other things to be sold? We can have a look if there's a relationship between that product and region. So maybe certain regions are going to be more impacted than others, so we can think about mitigation. Can we explore if that product's being provided in other parts of our supply chain so that we can deal with that? Or another example, we look further down the supply chain. So what happens if the supplier has a poor harvest? So we could perhaps be looking at, say, coffee beans or flour, for example, if we're making the pastries. And what's the impact if they have a poor harvest? And what we can do is we can go down the chain and we can explore what products are going to be impacted. Perhaps we can look as well in the area where there's been a poor harvest, because if there's been poor weather, maybe before we get information about that, we can start to make predictions about if it's going to impact other parts, other products within the supply chain as a result of this that we don't yet know about. What about if something happens to the distribution centre? Do we need to be thinking about rerouting delivery trucks to the ones that are not affected? Do we need to think about rationing products to certain stores which are less popular to the ones where that product is more in demand? So all of these examples that I've provided here, these are all thinking about not just the discrete entities that we've got here, so things such as the product or the customer or a location, but we're also exploring how those entities are connected to each other. So these are some highlights of some conceptual ideas we might think about. So what I want to do now is we're going to start looking at some scenarios that help try and group and identify ways to spot graph-shaped problems. So the first scenario I want to look at is, does our problem involve understanding relationships between entities? So this is very much the definition that we've been using for graphs. And let's look at an example here. And we've got an example where we've got three different types of entities. So we've got a customer entity. So a customer buys a product, and that product's part of a category. And the example that we've got here, we've got two different customers, and whilst they're buying two different t-shirts, so we've got different stock keeping units for those t-shirts, they all fit into the same category of t-shirt. And the example I'm trying to show here from a graph-shaped problem is maybe there's things we want to understand what's going on. So we may want to understand what combination a specific t-shirt is being bought with other goods. Maybe the thing that we care about is not necessarily the specific t-shirt. So for example, a red t-shirt or a blue t-shirt, but actually what we're interested in about is the purchasing behavior of products that are of category type t-shirt. And where this becomes interesting is we want to have a look at, well, what else is the customer buying at the same time or very close proximity to when they purchase a t-shirt? So just as an example here, so we've got Lisa who buys a t-shirt, but maybe Lisa also buys a pair of flip-flops, maybe she also buys some shorts, and she buys some sunglasses. And if we've got a situation as well, and we examine the relationship between those components for Jane as well, and Jane also buys a t-shirt, she also buys some flip-flops, and she buys some shorts, then maybe we can suggest to her to also buy sunglasses, because those would be the same sort of graph structures going on. And we can infer that maybe they're both going to be doing a similar activity, i.e. maybe going on holiday, or it's summertime's coming and they're preparing accordingly. And this kind of thing, this sort of trying to understand the relationship between the entities and what's going on, these are the kinds of things you'll see if you're looking at recommendations. So the example I just described here would be an example of the kinds of things you do for a recommendation system. Next best action is another example of this. So that, to some extent, is a kind of recommendation system. And the idea here being is if a set of actions always happen and produce a desired outcome historically, maybe you're going to go away and take that. And when you see these patterns happening, when you see those connections being made in a certain way, you can go away and start to recommend what should happen next. Fraud detection is another great example of where we want to understand the relationship between entities. So specifically, if we think about third-party fraud, where you have a group of individuals and maybe they're sharing personal details. So for example, maybe they are going to be cycling a home address, maybe they're cycling an email address, phone number, and other personal details as an example. And if you think about that data being stored in a table, it's not obvious that there's a connection there. But if we pull that out and we draw the connections between individuals and these elements of personal data, then we can start to observe in these fraud circles, we see these rings going on because they have a long connection to each other. And that's a really, really powerful way of applying a graph to be able to ask that question, to try and spot those patterns. Identity resolution is another example of this. So again, this same theme of being able to identify if, for whatever reason, because we've been combining systems or two companies have merged and so forth, and you have different customers with different names. Maybe the name's been spelled differently. Maybe you have initials for one and the full spelling for the other, and so forth. What you can do is have a look at what's connected, and if they've got shared email address and so forth, then you can use those graph structures, understanding those connections, to be able to help you do that identity resolution. And data lineage is another great example of this. So if you think about if you've created some kind of a data report or you have some kind of business intelligence dashboard, to be able to describe where your metrics have been sourced from and what transformations have been placed on that is really important. And this is a great example of a graph-shaped problem that you can solve when you're trying to determine the data provenance that you're working with. So let's move on to the next scenario. And that is, does the problem involve a lot of self-referencing to the same type of entity? So that's a bit of a mouthful. So I'm going to bring up a diagram example here. And what I mean by this is, yes, we're using the same entity. And I mentioned before how potentially if we're just using the same entity and the data associated with it, it's not necessarily a graph-shaped problem. This definitely is. And the way you can spot this is, whilst the data in this example here, we're looking at all of the direct and indirect reports for Jane, whilst that data may well reside in one table, the thing that we find ourselves doing is we keep referring over and over again into the same table because we have to keep doing these ID lookups to keep moving through. So this is this self-referencing that I refer to. And the thing with a graph is, again, this is about understanding the relationship between entities. And it's a lot easier to be able to describe this, where we can say, well, we've got our employee entities, and now we're talking about how they're connected to each other. And you'll spot this kind of thing in organizational hierarchies. So this is an example that we've covered here. Social influencers. So this is an example of where we may want to understand how people are connected to each other, and some people will have a greater number of connections than others. And if we want to understand who are the social influencers network, so if we think again about our coffee shop example, where perhaps we want to find out who are the social influencers who are a customer of ours, so we can target offers to them. And this is a great example of where we're looking at how people are connected to other people. So again, it's that self-referencing of the same type of entity. So that entity is person, but obviously those are going to be different people there. Friends of friends, this is another great example. So if we wanted to try and predict who may know somebody else, again, we're looking at the connections between different people. And just as an example, if you've got myself and maybe there's another person called Bob, and it turns out that I'm friends with Anne and Dan, and Bob is also friends with Anne and Dan, then there's probably a likelihood that Bob and I know each other because of those common friends. Again, the relationships between people that we know. And you see this in this kind of thing in Facebook or LinkedIn when it suggests contacts that you might know. And churn detection. So again, using this idea of influencers. So if you can understand in your network who are the influential points, and let's say, you know, that they are likely to leave your service or your network, then to try and reduce the number of people that they take with them or influence them to have a negative thought, maybe there's things you can do to target them to make sure they have a better experience. Okay, so scenario number 3. Does the problem explore relationships of varying or unknown depth? So let's bring up our example. An example we've got here is a supply chain type example. And on the left, you can see we have an organization called Pencils Are Us. And Pencils Are Us sells pencils. And those pencils are bought by an organization called We Love Stationery. So they're a stationery provider and they sell all sorts of stationery. And Pencils Are Us buys wood, so it buys a raw product of wood from We Sell Wood, which it uses to manufacture the pencils that it then goes on to sell to We Love Stationery. An interesting relationship between We Love Stationery and We Sell Wood is that We Love Stationery sells pens to We Love Wood. So what would happen if We Sell Wood, which is a small family-run organisation, they've decided, you know what, we're going to retire now, we're going to close down the business. What impact does that have? And this is a very simple supply chain. Maybe there could be many links. And we can see straight away that it has an impact on Pencils Are Us, because they're no longer able to source that raw material that they process. So they're not going to be able to sell pencils to We Love Stationery. But the interesting thing here is that you can see We Love Stationery gets a double hit. So no longer are they able to sell a product to We Sell Wood, but they're no longer able to source pencils from Pencils Are Us. And you can think about this as the example that we covered with our coffee shop, where what happens if our supplier has a bad harvest? So what is the knock-on impact of that? And as mentioned, this is the kind of thing you would see in supply chain visibility. You would see this in bill of materials. So for example, when you're building out, say, a car or a computer or something like that, where you're pulling in the different components, you can have a look at any impacts with regards to running out of certain parts. And you can see this in network management as well. So the idea that, you know, what happens if a certain, if a router or a firewall goes out, you can traverse down the network and predict what impact that would have. And the last scenario that we're going to look at is, does our problem involve discovering lots of different routes or paths? So we've got the last example here. And this is sort of a UK-based example. So if you were getting the train to Edinburgh from London, there are a couple of paths, there will be more, but there are a couple of paths that you can take. So you can either go up the west side of the country and you'll go past Rugby, Crewe and Lancaster to get to Edinburgh in Scotland. Or the other route you could take is up the east side of the United Kingdom, and you will stop at York and Newcastle and obviously many other stops to get to Edinburgh. And this is an example where we're interested in seeing, is there more than one way that connects two entities together, two discrete entities together? Is there more than one path? And this is relevant, for example, if we think about logistics and routing. So coming back to our coffee shop example, where if something happened to our fulfillment center, if we wanted to create new routes for our trucks to go to new fulfillment centers, if they now need to change the routes that they go down to get to stores because they're now coming from a different fulfillment center. So you get an example of the graph of the problem where we're looking at the connections between there. Infrastructure management is another example. So we kind of touched on this previously in the last scenario where we were talking about a dependency on a certain item, but this also fits in as well about trying to identify whether you have enough contingency. So as an example, if you've got, you want to make sure that if you've got an important component, you have enough redundancy in your system. So if that component goes down, you don't have mass disruption within your infrastructure. Or dependency tracing is another one. So as an example, if you have several applications that are running and they go down, you can go through and trace if there's a single point of failure that is causing that. So let's say, for example, a virtual machine that was hosting those applications went down. So I've gone through these 4 scenarios and we're just going to quickly recap those. So scenario 1, does our problem involve understanding relationships between entities? So this is the kind of thing we would see in recommendations, next best actions, and so forth. Scenario 2, does the problem involve a lot of self-referencing to the same type of entity? So this was the example where we're looking at an organizational hierarchy, and this is as well, you can incorporate things like dotted lines and so forth, if we're looking at friends of friends and so forth. Scenario 3, does the problem explore relationships of varying or unknown depth? So this is all about trying to sort of discover the unknown, where you know where your start point is, you know what your likely endpoint is, and the different routes or what your endpoint looks like, and being able to dig down those. And we see that kind of thing in supply chain visibility. And the last scenario, does our problem involve discovering lots of different routes or paths? So this is all about trying to identify all of the paths between 2 points. And we see this in logistics, planning, and so forth. So I think it's really important to think about sort of what can you learn more? So how can you learn more about graphs, and how can you in turn learn more about graph-shaped problems? So what I'm going to do is I'm going to go through some resources, and this is by no means this is not an exhaustive list. These are some that might be a helpful starting point for you to look at. So one thing I would recommend is the Graph Databases book. So it was released a few years ago, but I still think it is very relevant. And in there, it talks about why you would want to use graphs, and it explains in detail some of the examples where you would find graph-shaped problems and how you'd apply a graph to them. There is a chapter in there about how to model for graphs and so forth, so that's really good. You can download this book for free. So as a PDF, you can download it, and you've got the link over there on the right. If you prefer a physical copy, that is also available for purchase, so you can find that on your favourite online bookstore. So the next one that I find really useful, and the emphasis I want to put on this as well, is to be able to be better and get better spotting graph-shaped problems. You have to practice graphs, I think, and the best way to do that is to go away, read about them, learn about them, have a go at working with them as well. And a really great way to get started, if you're not familiar with working with graphs, would be the Graph Academy that we have. And again, this is high quality, free online training that you can do. We have a large number of modules, from getting started with Neo4j to how do you go about doing graph data modeling. We have stuff on there on graph data science, if that's something you want to move on into the future. So you've got a lot of great content there. And what you can do as well is, if you want to get some kind of recognition for the time that you've invested, you can also take part in our certification. So you can become a certified Neo4j professional if that's something of interest. So that's a free thing that you can go away and do. The exam is free. You can retake it if you don't quite make it through. So I would heartily recommend that you have a look at the Graph Academy online training, and if you're interested, to check out the certification as well. And last but not least, and again, we have many other things, we have blog posts and so forth, and if you're interested in finding out more about those, let me know. And we have our Neo4j YouTube channel, and this is a great place. We have a lot of content in there. We have online conference content, so we have online conferences obviously at the moment, but for example, conferences in past like Graph Connect, which is our big annual conference. We have regional Graph Tour events. We have meetups. We have many different places where we generate content, and these get placed onto our Neo4j YouTube channel. And here you will find things like how to do things. You will find information on best practices. And the thing that I really point to as well is there are many customer stories about how they've gone away and been able to identify and solve their graph-shaped problems. So there is a lot of talk on that. So that is a really good place as well to go away if you prefer to watch videos. So with that, I hope you have found this talk helpful. If you have any questions, I'm going to be looking at those shortly. I think Sabina will be asking those. If you want to get in contact with me, you do have my details there as well. So with that, thank you very much.
Thank you, Lou. Very interesting. So now let's take some of the questions we have here. The first one is about the example of the coffee shop. And the question is, would how the coffee is purchased be represented as another relationship or an attribute of the drinks relationship?
Great question. So I've given a very conceptual representation of what's going on there. And I think with this, it's going to be driven by what kind of question are we looking to answer. So let's just say for this example, I want to, the key question I want to know is customers' interaction with a coffee, as an example. And I'm not too worried about what the interaction was. I just want to know that that interaction happened. Then maybe I would just capture the fact that customer has a relationship to coffee, and then what the interaction looks like, I probably capture as a relationship type. Now, if, for example, I really wanted to know about all the different types of interactions that somebody can have with a coffee, so let's say I want to understand how somebody is, how are they using my premises? So I want to know, do they come in and pre-order their coffee? Do they come and buy the coffee in store? Do they then take that coffee and sit in store, or do they take it away, as an example? And then what I might do, depending on what kind of volumes there were and things like that, then what I might decide to do is I might create a separate node for the action, just because that becomes more prominent and something I want to research. So I hope that helps answer that question.
Thanks. So another question is a graph database the best place to do collaborative filtering?
Yeah, so that's a really interesting question, because effectively you're describing there about building recommendations engine, I guess, and one of the approaches you may use is collaborative filtering. So the really interesting thing with graph databases, so I've not yet, and one project I really want to test out is comparing graph database to other processes, collaborative filtering. But the really powerful thing about a graph database and collaborative filtering is you can do that real time. So if you think about certainly sort of machine learning pipelines that are used to do that, is you have to do some kind of a build of that. You have to run that process, and that can be a time-intensive process. And you potentially run into that problem that data, depending on how long it takes and how often you can refresh that data, might be stale. The really, really cool thing about using graph databases for collaborative filtering is you're effectively checking, that crossover checking, the intersection checking at real time when you run that query. And that's really great if you want to change what you recommend because maybe something's going low in stock, so you don't want everybody suddenly putting that in their basket. So you have that degree of dynamicness that you can do, and we certainly have many clients who, for that exact reason, are using graph databases for this.
Thanks, Lee. Another question which several people might have is, if we have a specific use case that we'd like to build on Neo4j, can we talk to you, Lou, or someone like yourself to build out a graphical model?
So what I would say for that, so by all means, you've got a number of ways of how you can do this. So, but I will definitely plug, so it wouldn't necessarily be me, but we do have a professional services arm of the organisation, and what they can do is, if this is a specific project that you're working on at work and what have you, and you want some sort of detailed help with that, they can come in and help you build out the model, and they can advise you with that kind of thing. If you're more of well, actually no, I'm doing this as a hobby and I want to understand more, there's something I'm really passionate about and I want to spend some more time, then what I would suggest you do is certainly sort of contact us in the community. So we have a very vibrant developer community. So that's community.neo4j.com. And what you can do is sort of post there what kind of project you're working on, what your musing is, and then we've got a very active and strong community who can come along and help you with that.
Thanks. Another question we have is, could you give an example of a relational problem that cannot be modeled as a graph problem?
Oh, so that's an interesting one. So what I would normally say is, I would always argue you can pretty much do anything in any tool. So if just as an example, if we had a highly connected data set and we had a graph problem, I mean, you could maybe be able to run that on a relational database. You'd probably have to throw lots of memory at it. Maybe you end up denormalizing your data model. Denormalizing your data model. So you kind of lose that benefit of it being in that normalized state. It becomes expensive if you need to update it. But conversely, I'll say you could go off and do what I would say a traditional sort of tabular, so your traditional table type question. So things like slice and dice my profitability figures for the past, 10 years or something like that, or do some kind of, run an average across down a column in my table to give me some values. So you could theoretically go and do that in the graph database. But the reason why you wouldn't want to pick, for example, your highly connected data for your relational database, because that's really expensive on memory if it will complete. And it's the same way, again, if you think about how data is being structured in, say, within Neo4j or in graph database, where because we're focusing on this sort of hyper-normalized view of how entities are related to each other, you have to visit each of those entities to pull that data out. Whereas if you think about it being stored in a table, you're literally just going straight down that column and running sums. So anything where you're looking at and this is where we're talking about, you've got sort of millions and millions of rows and things like that, and you're trying to do summation, then that is a great example of something you wouldn't want to do in a graph. You could theoretically make it work, but I'm always one for picking the right tool for the job. So if it's that traditional, I'm going to be summing a large number of numbers down a single column, that is a traditional sort of tabular type database job. If you're saying, I want to explore how things are connected and I care about how they're connected, then that is a traditional sort of graph database route to go down.
Thanks. Another question is, what do you recommend to visualize graphs?
Oh, so there are many, many ways you can do this. And I think, so the best way to answer this, so there are many tools. So some people, if you're just doing some sort of ad hoc visualization of your graph, maybe, for example, we've got Neo4j browser, which is like a sort of a developer aid. So when you're testing out queries, you can get sample data back from that. We also have a visualization tool called Bloom. So that allows you to do sort of near natural language exploration of your data. So the idea is if you're familiar with your domain, you don't have to write a query to explore your data. You just basically type things such as like the property names of your entities and so forth and what the relationships are. So that's an option as well. And these are really great sort of data discovery tools. Our partners have also produced tools as well. So Lincurious have a data exploration tool. So that's a great, visualization tool that you can use. Down to we're going to have, there's lots of libraries, and I apologize, I've probably missed some of our partners as well, but you have these these are kind of like tools that sort of sit on the database, and you may need to do a bit of configuring or setup, but effectively that's the data as is. You also have a large number of visualization libraries, so you'll have some partial ones, like again sort of thinking in our labs project we've got NeoVis, you've got other sort of like graph specific visualization library. So these are ones where they kind of take the knowledge of like your node entity setup, and then you just sort of say, hey, you want to display it, right down to people using things like D3 libraries to go away and they home build their visualization tools. So you've got a huge plethora of options. One thing I would suggest you do, if that's something that is of interest, if you go to our developer guides, so if you go to neo4j.com/developer, what you will find is there's a link there for developer guides. So if you click on that, you will find a link in there for visualization, and there you'll find information about the different things that are available. And there will be many more besides that as well.
Thank you. So looking at the time, this is the last question we can answer live here. The question is, do you need normalization steps with a graph database?
So that's a great question. And I think the best way to think about this, so for those of you who've come across it, you know how when you approach data modeling, you have your conceptual data model, you have your logical data model, and then you've got the physical data model. And conceptual data model is sort of thinking about, the scope of your problem, and you're probably going to have you're going to describe your entity. So let's come back to customer and coffee as an example. So we're going to say probably we've got a customer, and customer buys a product or something like that. So that's kind of like our conceptual view. And if we think about when we start stepping down into the logical data model, and this is when we start to think about adding properties. So for a customer node, maybe we're going to add properties such as a name, maybe we're going to add like the loyalty card ID, maybe we're going to put their email address on the beverage, maybe we're going to put something like, maybe it's got a stock keeping unit, maybe we want to attach something to it. Now, the really interesting thing when it comes to thinking about graph databases and how we put stuff in there, and I will caveat this a little bit, but a lot of the time, when you then go away and start building your prototype, or you start going away and loading your data into a graph database, you typically tend to sit at that logical data model step. Whereas if you think about traditionally, if you're doing something for a relational database, you're going to be stepping into the physical data model, where you're then thinking about, well, I've described the scope of my project, problem. I've now kind of sort of annotated a bit better, so the logical requirements model. So I've annotated a bit more about what kind of properties I want to be associated with that. And then when you go into that physical data model, then you're starting to think about, well, what do I need to do to model my data so that it is stored in the best way for my physical database. An interesting thing with graph databases is generally the logical requirements model stage. That's usually a starting point, and if not the finish point for many graph-based projects. Now, there may be certain conditions where you need to go down that route of where we also think about the physical data model for a graph. So there will be some iteration. So not necessarily how you'd think of normalization in a relational database, but you may sort of, for example, pull out certain nodes. So I don't want to go into huge detail with that. There's some situations with that, but that's a later down the route. but a lot of the time, most of the time, just stopping at that stage where you've annotated what properties you want in your nodes, what properties you want on your relationship, is that point. So the thing I want to touch on as well with sort of thinking about normalization in a relational database versus when you put data up and when you're putting data in a graph is due to the nature of how we store the data in there. So if you think about, I'm going to pick an example. So let's pick two people and they live at the same address. So I'm going to have one person node, they're called Anne. I'm going to have another person node called Dan. And let's say I've got an address node of 20 North Road. So if Anne lives at 20 North Road when I'm loading my data, then I create a relationship between Anne and 20 North Road. If I want to also say that Dan lives at 20 North Road, I don't create another 20 North Road database, North Road node. How I effectively recognize that cardinality, the fact that there's more than one person living at 20 North Road, is I create a relationship between Dan and 20 North Road. So I'm hoping this kind of shows, so you don't have that repetition of data because of the nature of if there's more than one, if the node has more than one connection to something, then what we do is we represent that through just creating those connections. So I hope that's answered that question.
Thanks again, Lou, and thank you to our audience for joining us today. Bye-bye and stay safe.
Thank you. Bye.